In this lab, we will analyze the motion of a falling object and observe how its motion differs from an object moving with constant velocity in a horizontal direction. Based on our observations, we will discuss the properties of a ping pong ball's motion as well as other factors that could have changed the result of the experiment. As with Lab 1, the experiment begins with a look at Newton's second law, which states that when a net force is applied to an object, the object will move a distance at a rate proportional to the force. Using this information, the new position as well as the object's velocity at that position can be predicted. What changes between this and the previous lab is that the net force is not zero, meaning that when an object falls downward, new varying and overlying forces are now present. Forces such as gravity and the drag force previously had no effect on the object as it moved horizontally. However, in order to accurately examine the object's motion in this case, these forces must be accounted for in each step of our calculations. When the experiment is ran, the ping pong ball falls downward at an increasing rate, showing a change in the velocity. The data obtained from this experiment can be compared to the computational model. While our code is highly similar to the one previously used in Lab 1, the changing force plays a larger role in each iterative step through time. The data from our experiment as well as from our computational model are plotted together to show a correlation in movement. The graph shows that the computational model serves as a good estimate for the motion in real time, seeing as the objects move exponentially and in the same direction. A computational model that does not account for drag was created in order to show how the drag force affects the object's velocity over time. In conclusion, the model serves as a good prediction for the object's motion when an object falls vertically. Some sources of error in our lab may come from bad measurements in real time as opposed to the circumference of the ball and the measurement from the ground, as well as some human error accounted for when choosing points for the center of mass of the ball in Tracker. There are also some miscalculations in the drag constant, seeing as trial and error was used in order to predict an accurate drag constant. As our lab comes to a close, we have some questions surrounding terminal velocity, which is a property of the drag force. Terminal velocity is reached when the drag force matches the force of gravity, giving the object constant velocity. So the ping pong ball, over a good amount of time, would move just as it would horizontally in the vertical direction. This can only be determined by the model if with the drag, since the model without the drag contains no variables. So the terminal velocity would be the same if an object was thrown initially downward as opposed to being released from rest. However, with a faster velocity, the terminal velocity can be reached more quickly. In order to show this with our computational model, a larger time interval must be used for that object to reach terminal velocity.